Hello, everyone. Welcome to another episode of the Day Zero podcast. I'm Spectre. With me is Z. And today we have a couple topics, including some game hacking, as well as some more YouTube bugs. We're getting back into some of those, as well as a little bit of hardware hacking.
Yeah, it's interesting to see another YouTube bug come up after very similar, completely different bug from last time, but also doing kind of the same thing. So I thought that was
Yeah, you have
interesting.
some similarities for sure. I was saying
Yeah.
that as well. We'll start off with a Synactive post on some game hacking, though. So this is a post that talks about Neverwinter Nights, which is a D&D-like game. They go into quite a lot of detail on how they analyze the attack surface and do some reversing the networking protocol and packet structure. They have sort of a custom protocol going on. They have packets that contain a magic, some CRC checksums for integrity checking, frame ID, and then these wrapped game messages. And those game messages contain a byte that indicates if it's being sent from the player, the server, or an admin, as well as a set of command IDs, length, and data stream. These packets are encrypted, though, of course, if you consider a case where the server can be malicious, this isn't really a big problem, as the server will have the keys to communicate with the players. They found three vulnerabilities. The first of which is when the command ID has the major field set to 2 and minor set to hex A. They don't have the proper names of a lot of these commands, but it seems to have to do with save functionality, and the response will contain a list of integers for the information on the saved character. Problem is the list size isn't checked, so the server could send a really large list of more than 8 integers and perform stack overflow. Although this bug isn't really ideal and probably isn't exploitable because stack canaries are in play here, which is a little bit surprising. Sometimes in games you don't really see stack cookies, but in this case they are a factor.
Yeah, because
And
they
because
do
this bug is a
have.
linear overflow, you are going to smash the canary. Sorry, go ahead.
Yeah, well, just, because cookies do have a very obvious overhead on every single, I mean, you'll compile, oftentimes they'll be compiled not on everything, but that is why you sometimes won't see it as it has that overhead. I do kind of want to mention that because I'm not entirely sure how much of an impact this had, but I imagine it did actually have an impact on the code base. And this is a game that originated in 2002 and then was re-released in 2018. So I'm not sure if the multiplayer LAN mode that they are exploiting here has code that originates back in 2002, or if they completely did the networking code, multiplayer was something they were adding. So I'm not sure about that, but this sort of bug here, I feel like that could also explain some of the decisions that are made,
Definitely
basically.
could.
So I wanted to shout out kind of that history there, but yeah, I'm not actually sure if when the code originated, because 2018 is a very different time than 2002, and obviously they will have done some work when they're re-releasing it, but there's also chance of copy and paste sort of deal. So just figured that context could be useful.
Yeah. But ultimately, because of the stack canaries, that linear overflow wasn't so useful. And that's where they get into the second vulnerability. So the second vuln was in the command where major was 5 and minor was 1, something for updating the player appearance. And the data blob would contain 10 indexes and values, and the indexes weren't checked. So they could be used to write out of bounds on the stack buffer. And since that's a non-linear out of bounds write, it could be used to just bypass the stack canary and overwrite the return address directly. Now, again, mitigations kind of came in play here because ASLR is also enforced. So exploiting this bug can't be done straight away. They did need a bug to defeat ASLR. And in a lot of cases with game hacking, that is kind of the big problem. It's generally not super hard to get like a write primitive or something because a lot of game engine code, particularly when it comes to networking, is sort of weak in that respect. But actually being able to defeat ASLR and get past that on 64-bit systems now is kind of the crux of the challenge. And that's where the third bug comes in play, which is this handle server to player message function. Problem is, if there's not enough data provided to satisfy the header, they have an int underflow when going to read the message because it'll subtract 3 from the length. So if you provide 2 bytes, it, int underflows, wraps around to a really large value. Um, And what's nice there is that the rest of the message is, which is uninitialized, will be read from an adjacent buffer, which can be filled via another command. That's because the decompression code for decompressing messages will write to this RX buffer that's next to it. And so an attacker can control the handler that is used to process a given message, which they can they can basically use a read related handler to leak out of bounds content and defeat ASLR, and chaining that together, then they can ROP. So yeah, it's fun to see when game hacking stuff works out in the context of a malicious server, especially when they take the time to bypass ASLR and everything. Like I said, that is kind of where a lot of chains die. So yeah, I
And
mean, this is a bit of an older game, and like you said, it has been ported up, and because of that, with the copy paste factor, it's not a surprise that some of these bugs exist. They are pretty straightforward bugs, but the way it's taken advantage of is pretty cool.
yeah, that was the thing on this one. I did feel like at one point I was going through like, oh, this sort of bug, like maybe we're not going to cover this because like the bug itself is, whatever. It happens all the time. We don't usually cover them. I did think the exploitation, integer underflows are always kind of fun to see, just because they lead to some fun situations when it comes to exploitation. It's a nice primitive to have with the out of bounds right. And yeah, taking it through there. There's also just the fact like they did do this in online mode. They did do it with online and LAN mode. Let me double check here at the top. Yeah, they do have a multiplayer mode, which they did not explore. They only took advantage of this on the multiplayer LAN mode. You probably wouldn't have control of the server for the multiplayer online mode, but still, I mean, going for the LAN mode is fair enough, and also a little bit easier to do research on than trying to deal with the actual live system.
Yeah, I was kind of curious on your thoughts of the approaches they took here, just because it does probably have a little bit of overlap with some of the work you've done, right? I know you've done that work of reversing the messaging between the server and the client for games before, and have
Yeah,
had to deal with some of those challenges.
yeah. The main thing is like with the work that I did on an old game, uh, we didn't have a live server to work with. So there was no,
Yeah.
oh, I'm just going to like intercept it or like hook it as they did in one case, I think. For the crypto stuff. I think they were hooking in the server. I didn't have those options. I just had to reverse engineer and be like, okay, the client's expecting this, this, and this. Therefore, try and send those things. Like it was a very different process. It's so much easier when you have a live server to work with and like you could see exactly what it's actually sending. That's why I don't know how much of our audience would be doing this, but taking packet captures is so valuable, especially if you're able to deal with any layers of crypto on top of that. It is so valuable when it comes to trying to recover stuff. Yeah, I mean, without that, it's a lot of painful reverse engineering to do it. Yeah, they didn't have to really deal with the same sort of struggles here, and they were able to jump right into it. I don't think anything's really notable in their methodology. I mean, hooking it to get around crypto, or like hooking before the crypto's applied and after it's taken off, is pretty standard practice. So yeah, nothing really stood out on that front.
Yeah, fair enough. But yeah, once again, a great Synactive post, and when we can touch on game hacking, we like to, because uh, it's always fun to look at. But yeah, we will move on to some of our other topics. So up next from Tobiah Rai, I might have said that wrong, apologies. But it is an attack on Android Chrome, where attackers could take over PassKey's accounts over Bluetooth via FIDO intents. And this is a little bit interesting because I don't think we've talked about passkeys too much on the podcast before, at least not in the context of, them being attacked, or like implementation of it being attacked.
Yeah, you're exactly right. We have talked about passkeys both like when Google and Microsoft and co all made their big announcement of support for them. We gave some attention on that. We've talked about it in general. I am a fan of passkeys and the concept of passkeys. The practical implementation and vendor tie-in, not so much, but that is slowly being resolved. But yeah, we haven't really talked about vulnerabilities and actually trying to attack passkeys. And this is, yeah, like I said, kind of going more implementation, higher level. It's not like attacking the crypto involved here or anything. It's more just showing like So one of the main benefits with passkeys that has been touted around is the idea that you can't be phished if you're using passkeys, because the browser is doing a lot of the enforcement here. It's saying like, okay, this website is asking for a passkey for this user. So like it can't give you the passkey for, well, it shouldn't give you the passkey for some other domain. There are origin rules and things like that, but it
I was
should
gonna
basically
say,
shouldn't. Go ahead.
I was just gonna say it might be worth covering a little bit about what passkeys are, like just how it works a little bit, for anyone who might not have that context going in.
I mean,
You
the
know,
super high level thing is they actually have the summary, a very brief summary towards. I guess that's not towards the end; it's like a third of the way in. But WebAuthn is just SSH private key pub key for the web. That's ultimately what's going on here. Is you're having a device storing a private key and you're using it to sign challenges from the server. There's some logic around that and the challenges, so like you can't, so the browser enforces some degree of like phishing protection, and so you can't like hand your credential over to the wrong domain and stuff. But ultimately it is using stronger crypto for your keys rather than just a password. It's using actual like public keys, so you can't, even if you got the challenge response and somebody captured that, like even if the network were compromised, the account still wouldn't be, because public key crypto. So yeah, taking advantage of some of that. And one of the design things there is, of course, if you're dealing with the key, you've got to maybe share that around a little bit. That key is supposed to be fairly secure. Like users, unlike SSH keys, you can't just like copy them around and be like, oh, here's my SSH key for this, so I'm just going to copy it onto my other device and this other device and do all of that. You don't have that same sort of direct management. That's where kind of vendor lock-in comes in, where like Microsoft and Apple and Google all have kind of implementations of this. Google, of course, built into the browser, but also Microsoft, like, and Apple do built into the operating system. And Google also with Android, of course, so built into the OS there. And so you're kind of, the keys themselves are abstracted. It's just they're stored, in theory, they're stored securely, especially if you've got a device like a TPM module or like a secure storage area. It can use that. The gist of it is passkeys are supposed to be like a high security crypto key. You don't have direct access to it unless you're using some managers. Most managers don't, but you can like do it in like 1Password supports passkeys and Bitwarden supports passkeys. So like there is some way of getting access. Anyway, trying to jump back to the actual post here. You're not supposed to be able to phish them. That has been kind of a big issue, and what they try to take advantage of is cross-device authentication. So like I mentioned, this is something where like Apple and Google, their mobile devices, so what if you need to log into something on your computer? They have a whole flow, and I'm not going to go into the details of that flow. They've got kind of an example here where use your phone or tablet to scan this QR code on the device that has your passkey. So I want to log in on this. I'm going to scan this QR code with my more secure device. It's going to come up with a FIDO schema or FIDO intent. So that gets handled by whatever the password manager, whatever's handling the passkey is going to do that. It's going to do whatever the challenge is. So if that challenge is like, it's going to do the signing and all of that's going to happen there. And then it's going to communicate the response over Bluetooth. So phone gets that QR code, FIDO link, and that's going to have information for the Bluetooth connection that's made. And that is Bluetooth low energy. So that's not your normal going through your full pairing like you'd use with if you want to like stream audio to like a speaker or something. It's not that full Bluetooth. Low energy is a always on sort of thing. Like even when you turn Bluetooth off, Bluetooth low energy is usually still available. Super low power of that. And that's kind of what the limiting factor on passkeys is supposed to be, is this idea that, well, somebody needs to be like physically around when you're going through this cross-device login flow. Somebody needs to be within Bluetooth connection range of, or Bluetooth low energy range of you. And over that Bluetooth connection, so the two devices connect using information of the QR code. Browser now communicates its challenge for the authenticator to be, or like to get signed, and the authenticator sends the data back. And then the browser kind of wraps everything up since it initiated this, and you get your login. That's kind of your normal flow. I've explained this poorly. We went into more detail in the episode where we are. Actually, I'm not sure if we talked about the specific Bluetooth flow, but you can look up WebAuthn cross-device authentication and get like all the details if you want on this. In summary, like the core security of this is just you need to be in Bluetooth low energy range at the time and like actively listening for this connection, or actively participating in this connection. And that's going to limit like a lot of attacks. So you can't just do this over the internet. You can't just be like, yeah, do this on your phone and read me this value. Like it doesn't work that way. You literally need to have physical proximity. Nonetheless, if an attacker does have physical proximity to their victim, the attack that they kind of present here is, an attacker could have their attacker controlled page. They can have some page, victim visits it, and they click this link, and the core vulnerability that they found is just websites will let you. Like I can just create a normal link and be like, yeah, here's a FIDO challenge for your banking website. Please sign this sort of thing. And to be fair, you're like that attacker website is not getting the response. They're not getting the challenge, the signed challenge back, because like I said, the browser is not going to send it to like the wrong origin. So they're not getting that. But by trying to do this over Bluetooth, if the attacker then has like the Bluetooth device that it's pretending to want to connect with, basically you're tricking the victim into connecting over to your Bluetooth device. And so there's a big ask here of victim needs to visit your attacker page, need to click the link, you need to be physically local to them with Bluetooth to do this. Like the security of this passkey sharing depends on the Bluetooth. So they basically just come in, sat in on the Bluetooth and been like, I don't want to say they've broken the assumption because the assumption still holds. You have to be physically local to the victim in order to phish them. But you can indeed phish them. And it's interesting research in that sense. It's just not necessarily unexpected, I guess is the way I'd put it. Like, you can do the attack. They also call out, sorry, Spectre, I'll let you talk in just a moment. They also call out like the Bluetooth range here being less than 100 meters. 100 meters is a really generous estimate, I think, when it comes to like that is assuming there's no, like basically you're in an open field, your device, like 100 meters is a line of sight between the two devices. You may be able to get the 100 meters, even that's going to depend on various other factors surrounding signals.
A lot of environmental factors come into play there, yeah.
Yeah, like I haven't tried to test, especially low energy Bluetooth, but 100 meters feels like quite the distance. But it does, like for a lot of people, the main attack is they're going to enter their password on the wrong website. So requiring the attacker actually be physically local to you in doing this attack, that is a massive security step. It's still something that can be done, and I think they're showing here that it is indeed viable. Not the most practical, but it is viable. Like I'd believe it that like if came out somebody did this and like some specialized hack, I'd buy it. But I don't feel like this is necessarily going to be a big threat for absolutely everybody. They kind of call it out like, running a fake free airport Wi-Fi or something of that nature. Where, yeah, I could see it. I could see,
you can
maybe
see like
getting
a Hollywood style attack of it, like,
yeah, that's a good way to put it. Like, it's an attack. It's kind of the attack that was thought of though in the design, and they're like, we're okay with this risk. It's better than where we're at. Yeah.
I mean, so the Bluetooth part is important there. That said, the main angle that they were going for here and what they were trying to get fixed and was ultimately fixed was just like the browser just following those intent links arbitrarily. Um,
Yeah, that's
so
kind of
that
the
is fixed on
crux.
Chrome. I believe it's also fixed on Firefox now as well, if I remember when I looked into some of the reports. So
Yeah, the following of the intents is kind of the crux of this. It's where the browser's letting just a random website be like, yeah, do a challenge for this domain. Like, there's no purpose in that. Website, maybe for their own domain, it might make sense, but even then, usually you're going to expect this to come out through like the other flows and not a website. So, yeah, it makes sense. A patch was really just blocking it. That's where it comes down to. But still, it's an interesting sort of attack, and yeah, it's not even something you could do now because of the intent not being allowed off websites. So, fair enough, or good shout for mentioning that, but like as an attack, I don't know. I had really mixed feelings about this because I do like it, but it also feels a little bit like this is exactly where they're expecting there to still be an issue. It's this physical proximity sort of thing, which is a massive ask compared to just phishing somebody.
yeah, it is cool though, like getting some of the research there on passkeys and looking at it early because you know, as far as authentication mechanisms go, passwords are going to be around for a while. I don't think we're going to see a mass switch from passwords to passkeys. It's just adoption is slow, right? So looking at these issues and trying to like mitigate them and have some defense in depth in place before the wide adoption is a good thing. So
Yeah, and I mean, even a lot of places you can't just exclusively use passkeys. It's like you've still got your password as a fallback, so
yeah,
passkeys are just kind of like convenience. And
passkeys
I
aren't even the weak link. Yeah.
I will say, since
Uh,
I was kind of saying that I like passkeys, the main thing that I actually like about passkeys is this idea that every device you want to use to log in would have its own passkey or could have its own passkey. You could also then revoke the device's access, not
yeah.
just to your session, but I could be like, oh, well, yeah, I want to let my friend log in on my Netflix account or something. You can give them the key, you could take away the key. You're not sharing your actual credential, you're sharing something that lets them access, but can also be managed and controlled. So
Yeah.
there's that sort of aspect that I'm kind of, and of course, just SSH keys or public key crypto. I do like also, but yeah, it's more some possible functionality that I'm a fan of. That said, in practice, how Anywhere has actually implemented it hasn't really followed what I was hoping. So, bit of a letdown there.
Yeah. So continuing on web, we also have a post on disclosing YouTube creator emails for a $20,000 bounty. So as we kind of remarked at the beginning of the episode, this is pretty similar to the recent YouTube topic we covered, sort of going for the emails again and abusing some weird API quirks. So the post starts off with talking about an interesting behavior that was noted in Google's API, where due to some leftover debugging functionality, by sending a parameter with an unexpected type in a request, the response would contain this little error blob, which would contain it would basically state that the parameter given is of the incorrect type and what the type was that was passed in. And what made this particularly useful is that Google's API supports more than just normal JSON requests. They also support proto-JSON, which is the combination of protobuf and JSON. And with proto-JSON, you could pass an array of values which it would then try to slot into parameters. So by just passing an array of integers, for example, you could get a response that tells you all of the parameters that are getting parsed if they fail to parse due to a type issue.
I actually want to touch on what you just said, where they're able to leak the whole protocol. Like, if you're unfamiliar with protobuf, it is effectively just like an arbitrary format or like a way of formatting arbitrary data that can then be parsed into structured data. So protobuf will like do code gen for like C++ or Golang, number of other languages. I don't use it. I mostly have used it on C++, but it supports a ton of different languages. So what you have to do with that is you define like the whole protocol there saying all your different parameters that it can parse into. And every parameter, you can't like rename them. You add like a parameter and you deprecate an old one. That way things can always kind of process even old messages. So this is kind of like if you've used like param miner trying to get web parameters. The power of this sort of attack specifically on JSON plus protobuf is the fact that you don't need a mine for the parameters. You don't need to brute force it or fuzz it at all. You're just able to leak every single parameter out, which, you know, is one of those cases of like, that is a very useful debug situation to end up in, basically. Like, it's one of those cases where on its own, like, this isn't much of an information leak, but for an attacker, this is a lot of really useful information that on its own isn't a vulnerability, but is still very, very useful. So
Great
yeah,
step in the chain. Yeah.
yes, I kind of wanted to really call that out because I think that is really cool that they ended up with that. It's not super common that you actually get that much information, but it is cool to see that.
Yeah, and even though it's not super common, getting it in Google API of all places where, you know, Google has tons of different products that are running off that, I mean, yeah, the value is incredible. So getting into the bug, when they were looking at YouTube Studio, they noted that the earn functionality, uh, when you went to that page, it would send a post request to this get creator channels endpoint, and it would return some data about the account. And you could also use this to get some limited information on other accounts as well. You basically like pass in these masks of what information you want. And if it wasn't for your own account, you were kind of limited on what masks you could pass. But using the earlier mentioned trick, they discovered a sort of hidden parameter called include suspended. Now, what the purpose of this parameter is, I'm not totally sure. But if this parameter is specified to true, it would return the channel's content owner association, which includes the content owner ID. And that's because the creator's earn dashboard and the content ID system that YouTube has for organizations to file copyright claims basically share the same code base. It's just like a slightly different front end. And because of that, the content owner ID could be passed in a request to this content owners list API endpoint, which would return a conflict notification email. Now, obviously, that's intended for the copyright claims and, you know, conflict resolution and stuff with that. But because there's that shared nature of it, you could also use that on just if you have an account that has monetization enabled, you could use that endpoint as well and ultimately use that to leak a user's email given their content owner ID. So quite a cool flow there. This ultimately netted a 13K bounty. So as always, you know, Google's pretty generous there with their payouts. Now, obviously, you know, it is just getting the email of an account, which you might not think is a lot, but it seems clear that Google has put a lot of effort into trying to mitigate attackers doing just that, because that's also what the previous YouTube related post was going for as well, was the same end goal. So yeah, very interesting attack. And as you said, the most interesting part is definitely their ability to leak the parameters because of the leftover debugging functionality with Google's API there, and giving you a notice if you pass the wrong type for
Yeah,
parameter.
yeah. When it comes to the actual leaking of the email, it is interesting that that endpoint, like the content ID stuff, when they're talking about using these APIs, they are just using like YouTube's API Explorer. Like YouTube has obviously all their applications, but they have an API Explorer. If you've ever hunted on YouTube, or if you've actually just, if you've ever tried to build anything on like Google APIs, you have probably visited the API Explorer because it basically just has all of their public APIs with a little web form that's super convenient to use, and like you can fill out, like gives you a very nice form and everything. So they were using that for a lot of this, but I thought it was interesting just that this content ID requires that you be like a content owner, which is, I guess they kind of treat it, seems like they're treating it as like a step up from your content owner, and that, or sorry, you're like a creator, just like you have a YouTube account, you've uploaded something, then you've got your IVP accounts, the individual video partnership. That's just like your monetized accounts. Like I think it requires you hit like 4,000 subscribers or something, like have a certain amount of watch time or whatever. And then you've got the content owners who are supposed to be able to use this. And it's interesting that they do let the lower level account actually hit this. And that was how they fix it. It's just like, you actually have to be a content owner to use the content ID API, which makes sense, I think. Like, you don't have a lot of need for that if you're not. But yeah, it's just an interesting situation of like, it's not a case of anybody could use this API. They called out they had to use a friend to make this request to see if it would work rather than just being able to make it. Like, it's not a case of like if you know the right URL, you can just make the request. You still needed some level of privilege or some level of permission there. And yeah, leaks the email. Google pays out a good bounty for, which I think is fair because people oftentimes, people have an email that may include like their name, especially when they're using it for like their login on like YouTube or something. Very well may have a lot of history behind that, like something they created many years ago before they started creating, then creator gets popular, still using their own account though.
Yeah, it can have some fairly substantial OPSEC impact on the victim.
Yeah. Like, I
Yeah.
do feel like creators are a targeted group of people where this does kind of matter, especially because the email can itself give some sensitive information. Not always, but it can.
Yeah. And it's sort of funny because where you were talking through there, the fact that you needed some privileges, you couldn't just use any account. You had to have an account that had monetization enabled. It's funny because on like most other websites, that would be a big deal and would take away a lot from the attack. But because it's YouTube and Google, and realistically, it's not super unheard of or like unrealistic for an attacker to have that scenario where they can get a monetized channel, whether that's by, hijacking another account or just creating one themselves and kind of building up that account. While there is that high level of access needed, because of the scale that YouTube operates on, it's still pretty significant, the impact. So
Yeah.
it's something that's only really that impactful because of Google's scale. So it's, and that's why it's a great target to look at too. All right, so continuing on, we have a post about Azure from Binary Security, and I'll let Z get into this.
Yeah, and this is just honestly another kind of fun little issue and bit of an oversight in design, perhaps. It comes down to API connections in Azure, so you can set up these API connections. And the idea being that you can set up a connection so that you can communicate so the API can communicate to other APIs for the most part. So you might set up a connection to like your Jenkins, to Defender. They call out they call out Jira, not Jenkins, Salesforce, or to your Key Vault or whatever. Like, you could set up arbitrary connections. These can go to any sort of thing as long as you can like give it information on authenticating and stuff. So whoever creates that is going to create this connection that exists, and then people can use the actual API connections, API, or like the Azure API, to make requests that might use these connections, that might take advantage of this. So basically, you're sharing access to the API without actually sharing the credentials to it. You're not being like, here's the actual authorization header or whatever secret key. It's, the API thing, the connection handles that, and then users might be able to access certain things through it, or certain things they try and access will make requests through it. It's not so much meant for users, I think, to directly call into. Anyway, what they ended up finding was that there was this endpoint in here, extension/proxy. And if I can type. What was interesting about that is this was an undocumented endpoint that effectively seemed to just pass the request through as a GET request through adding the authentication to it, to whatever endpoint you want, acting, as the name would imply, as a proxy to your actual connection, which meant that somebody who was just a reader on this and shouldn't be able to actually make any modifications could make requests directly to this proxy endpoint. And if there were any GET requests that would result in changes, and being real, a lot of APIs and websites still do that, where they'll either directly just accept a GET request. It's like update ID or update something, and they'll just use a GET request for that, and that's totally fine. Or they'll, accept like a URL parameter that changes the method or forces that. Like, there's a lot of ways, GET requests can still be vulnerable. And yeah, so it just comes down to this fairly insecure design of having a generalized proxy. And I believe the point of this was more so that internally things could end up calling it rather than meant to be directly used by users. Like the intent being more that your other services running inside of Azure may connect through here, not so much a user's going directly. So I believe the way this got fixed, yeah, here it is. Microsoft fixed the API connection vulnerability by not allowing any requests through the extension / proxy, except for test requests, which is kind of the thing that they found this through was test requests had used this to like test uptime, test whatever. I'm not sure what was actually being tested there. Just had the test request field to test the connection at the very least. So basically they just blocked it except for that. So that is pretty much what you would have expected it to be in the first place. Like this whole proxy, I've seen one of the places I see the proxy set up a lot is S3 buckets, running a proxy endpoint in front of an S3 bucket. And quite often you can get requests, at least going to other endpoints. This is just like a much more extreme version of that. Although I guess you're not able to do arbitrary domains, but you are able to have more or less arbitrary endpoints depending on the configuration. So yeah, I thought this was just an interesting bug because one, I just wouldn't have expected Azure to go with that, like just straight up, yeah, let's just have a proxy existing there when that wasn't really what was needed. I understand where a developer would think of doing the proxy because they don't know what endpoints are going to be needed to do this sort of test. So it kind of makes sense, but having that functionality on its own just kind of raised the red flag for me. Of course, it wasn't an obvious functionality. This wasn't a documented API or a documented endpoint. They just noticed it being used. But yeah, it's a cool find.
Yeah, I can't point to like particular examples, but I feel like this sort of pattern seems to be somewhat common in cloud, just because of the complexity, I guess, of what can be needed.
There's a lot of use of reverse proxies, and that's in a sense that's kind of what you're doing here, just in a much more limited way by putting it behind an endpoint. But yeah, it is pretty common now because you have things running all over the place on all these different, maybe even across different cloud services. Maybe they'll all be in the same, but you have things running everywhere across different domains at least, that you just want to glue things together. And so rather than writing, say, a dozen endpoints that all kind of just change the request URL a little bit, like, oh, this one's going to this place, this one's going to this endpoint, you write like an extension, or sorry, not an extension, you write a proxy that can go to any of them, and it's like overly powerful but super convenient on the developer because now you just need to call that proxy endpoint and you're good to go. You don't need to write like a bunch of endpoints to do every functionality you want.
Yeah,
like it's the same thing that kind of drives towards like I don't know, now that I'm about to say it, I feel a little bit like maybe the connection isn't as strong as I think, but in my head, I see a connection between something like doing this and like all the deserialization bugs, where it's like, you just support like arbitrary data types because that's just super easy to do, and you never know what you're going to want. Like in my head, I see a connection.
I can understand that perspective. To be fair, I can see like why you would make that connection. Yeah.
But yeah, it's a fun issue. I think it's a cool find. It's kind of hidden there. It's like, yeah, if you're just looking deep at the application, you end up coming across, oh, this can be abused.
Yeah. So that's most of our topics of the episode. We do have a few shoutouts, the first of which was from Portswigger, and is called SAML Roulette, the hacker always wins. And this touches on an issue that we covered previously from GitHub Security Lab, and it was the bypassing SAML SSO auth with parser differentials. That was when you had two different XML parsers in play, where you had RexML as well as Nokogiri. And Portswigger had put out a post because they had collision on this bug, but they had actually exploited it a bit of a different way. So Z, I know you found this one a bit interesting. I'll let you talk about what you found interesting from it.
Yeah, if you like that sort of bug, they provide more details here about. So they actually kind of call it out here while researching that this being some of the Ruby SAML stuff. While researching this, GitHub independently discovered and patched vulnerabilities. Their disclosure omits key technical details, including the specific mutation and how to exploit without authentication. We believe in sharing the full details on how these attacks work. So rather than kind of covering the similar bug again, they provide more of the attack information, attack details, that you can take a look at. It seems like they do take actually a bit of a different route, although maybe it is just because of something lacking information. I'm not sure on that, but they include some more details, so it is worth checking out. In addition to, we were just covering this like last week, wasn't it? Like
Yeah,
I'm
it was
pretty
last
sure
week.
this was just our last episode.
Yeah.
So yeah, I just include that along with episode 277. Going to cover this, but yeah, it's very much the same issue, so we didn't want to cover it again, but they do add some details
Yeah, and
and
you get a bit of
some,
that different perspective.
yeah.
Yeah. So the other shout out that we have is a post by PT Swarm. It's called Last Barrier Destroyed or Compromise of Fuse Encryption Key for Intel Security Fuses. So again, this has some overlap with something we covered previously. It gives some more background and details on the bug we covered in episode 255. And it's about Intel's CSME or Converged Security and Management Engine and how they were able to dump the root keys of it. They go into quite a bit of detail on how that works and the main elements of the root of trust, which are these secure fuses, which contain encrypted key material, as well as the fuse encryption key that's burned into the ROM, and that is what's used to decrypt the material that's in fuses. A lot of detail on how the key management scheme works and that whole flow, and a fair bit of background on like how they use the fuses and how you could actually, you know, observe the fuses with like scanning electron scopes and all of that, which is cool because while that's kind of, that attack's been around for a while. It's been quite a while. I think that fuses have been encrypted specifically because of that reason. That you can kind of gain that introspection through hardware and spending lots of money. But still, it's not something that's talked about too often, and it's in an area that has a lot of NDAs and trade secrets and stuff. So Intel and AMD and these companies don't really talk about these systems at all and how they work. It's kind of in their interest to keep that all secret. And so when someone else is able to dig into and get this much information about how their setup works and publish it, I mean, there's just a wealth of information here if you're interested in that stuff. I didn't want to do full coverage of it because, for one thing, I have a bit of familiarity with how this works in AMD because I've kind of done a little bit of that research myself. It is a little bit different with how Intel does it. And because of this area being so like low level and not a lot of stuff being talked about, there's a lot of acronyms and stuff being used here that would make it a little bit difficult to cover in a comprehensive way. So if you're interested in these security engines, I think this post will be a great read for you. They cover two different attacks, one of which they didn't really talk and is kind of what we talked about before, where there was a hardware flaw where the fuse encryption key could be extracted before the key is cleared. And then they also talk about another attack where they sort of use voltage glitching to get into a more useful state, like they get into a red unlock state. So yeah, I mean, like I said, a lot of really cool information there. They also have some diagrams and stuff that clarify how their setup works. It's a great post if you're interested in that. So wanted to give that a shout out. But yeah. So yeah, that's pretty much everything we have for the episode. Unless you have any parting thoughts, C, we'll wrap it up there.
Yeah, no more shout outs.
All right.
That's good for the week.
So as always, thanks goes out to everyone who tuned in, and we will catch you on the next episode.